I'm just working to warm you up to scary things. All right. This is even scarier. You ready for some really scary thing? But scary, but beautiful. I want you to see both that what I'm about to do now is both scary, but is so, so incredibly beautiful. All right? I want you to be able to see the beauty in this. All right? All right. So this guy, you guys are studying, you think this 1090 stuff is really dumb, right? Why would we care about sentences like this, right? They don't, okay, they say a few dumb things, but who cares? And we're going to say, no, actually, these four storologic statements are hugely, hugely expressive. All right? I ain't going to make a bold statement. I don't like universal statements, but I'm going to make a bold statement that you name any mathematical statement. And if you want to understand that mathematical statement, the best way to do it is first write it down as a first order logic statement, predicate logic. All right? And then you take Jeff's 1090 course and you learn the rules of adversary and provers, and you learn the structure of how to prove it. And it'll help you understand what's going on. All right? But here I'm going to give you another example that's really amazing. All right? So I'm going to define a logical sentence that called compute that has 3 free variables. All right, so what do I mean by this? I'm going to tell you right now ahead of time, we're in the universe in which we have integers, and they're all positive integers, and we have plus and we have times. All right, so that's the universe we live in. And I'm going to give you a logical statement that looks kind of like this. It's going to have for alls, it's going to have exists, it's going to have times, it's going to have plus, it's going to have less than and equal to, it's going to have equal to, right? That's all it's going to have, right? And it's going to have some free variables. Remember here, J and I, right? Right, so all the variables, X, I, J, right? All of them represent integers. Right? The only operators are these guys here. We're going to have 3 free variables, right? It's going to represent some J, some I, and some Y, right? Free variables mean they're not quantified. And what do we want is you plug in integers for those 3 variables, and sometimes this sentence will be true, and sometimes it'll be false, right? For some integers, it's true. For some integers, it'll be false, right? Now, here's an example. Here's a sentence, right? And if you plug in J to be bigger than 1,000,000, then the sentence is true. If you plug in J to be smaller than 1,000,000, the sentence is false, right? Everybody with us here so far? All right. Now, here, let me tell you something else. This is all about interpreting things in different ways, all right? So J, what do I want J to be? I want to think about J as a Java program, right? Because you all write in Java. J is a piece of Java code, right? And I is an input to that Java code, and Y is an output, right? But I can take all of those things and I can code them as integers, right? So let's do an example. Here's a piece of Java code. What does it do? You're given an input I. If I is how are you, then it outputs fine, thanks. If I is not how are you, then it crashes. All right, it's a piece of Java code. Well, I can interpret that Java code, well, as ASCII. And as soon as I turn it as ASCII, I can treat it as a binary string. And as soon as I treat it as a binary string, I can convert that binary string into one big integer. Right? Everybody agreed with that? All I'm doing is I'm taking this text, these characters, I'm treating those characters as ASCII. I'm treating the ASCII as a binary string. I'm treating the binary string as an integer. Right? Everybody agree? Good. Now here is an input. The input is how are you? Again, I can treat it as ASCII, which I convert into binary, which I convert into an integer. Right? Everybody good with that? Right? So here I have two integers. And here is an output. Fine, thanks. I convert it into an integer. Now, let's take my thing called compute. It's a first order logic statement, right? If I plug in these values of j, I, and y, then, well, look at this Java program on this input outputs that, right? So this Java program j on input I outputs y. So I'm going to say, so this sentence is going to evaluate to true. Right? Does that make sense?
Jeff, I have a question.
Yeah.
When you convert this the binary string into an integer, is like sometimes would it be more helpful to like turn to like a prime number or something, so you don't get like two strings that are different, right. But would we have to do that, or is that unnecessary?
No, I think that's unnecessary. I think if you do Google for ASCII code, if you don't know ASCII already, it converts every character into a hexadecimal, right? Oh. And then every hexadecimal is a string of binary, and then then we use binary notation to convert it into an integer.
Oh, gotcha.
Right? Really straightforward. All right. So you plug in these integers and it gets true. But if you plug in these integers here, what did I change? I changed y to horrible. So it's a different integer. And now the answer is false. Right? Everybody get that? All right. So this seems like a miracle first order logic statement, right? It's all built with for alls and exists. Yet it's going to take a Java program integer and tell you what it does on this input, right? That's pretty, what you agree, everybody agreed that that's amazing, right? And what's even more amazing is I'm going to tell you how to do it right now. And I'm hoping I'm going to tell you in a way that you more or less understand it. All right. Any questions? Yep.
So why is it false again? The bottom part where you wrote false?
Oh, because if my Java program is this, and my input is how are you, then if you read the Java program, the output should be fine, thanks. The output is not horrible.
Okay, I see. So like the number you got, like this big integer, did you make that or you got it as an output?
This,
like, yeah, this one.
The J?
After the binary number, the number like 3, 4, 5, 3, 5, the big number.
Right.
Yeah.
The truth is I made that up randomly.
Oh, okay.
Right, but let me tell you what it's supposed to be. Maybe I should make it randomly.
I thought it should be the address.
No, maybe I should do this explicitly and show you how it's actually done. The first character is an S, right?
Yes.
So I look up the ASCII table, what an S is. And S is some character, right? S is some binary string.
Yes.
And T is some binary string. And R is some binary string, right? So I take all those binary strings, 16 bits each, and I concatenate them together to get me a binary string.
Okay.
And
yeah,
then
I did it now.
Right, and then I convert that into an integer. The reason I didn't spend much time on it is because it really doesn't matter, right? There's some way to encode this string into an integer.
Yeah, okay.
Right? All right. So here, let's relate this back to what you're supposed to learn in 2001, right? You're supposed to learn that the halting problem is undecidable. What's the halting problem? I give you a Java program and I give you an input, and you're supposed to tell me whether that Java program halts on that input, right? And that's the halting problem. And what's the bad news? The bad news is that the halting problem by Turing, you know, is uncomputable, right? We're going to prove that either today or on Thursday. Then, well, if the halting problem is uncomputable, then it's uncomputable to know whether this compute thing, it's uncomputable to know whether J on input I outputs Y, right? It's uncomputable. And hence it's uncomputable to know whether or not this first order logic statement is true or not, right? I give you a first order logic statement, like, and I want to know over the integers, is it true? And that is an undecidable problem. There's no algorithm, right? We're teaching you 1090 to tell you how to prove things. But what they haven't taught you in 1090 is that they're trying to make you do an undecidable problem. There's no algorithm to complete 1090. Right? Does that make sense? Any questions about this page?
For the halting problem, if the program is running forever, does it mean it's uncomputable too?
The input J may run forever, but if I'm going to compute the halting problem, the problem that's deciding it needs to always stop and give you an answer, right?
Okay.
We're going to get to the halting problem later. Let's focus on this computing problem, right? Right, so here's another question. Is there a proof system, right? In 1090, I'm teaching you proof systems. Is there a proof system that completely understands the integers? No, there's not. There's not one, right? That's Gödel's incompleteness theorem. He proves that given any proof system, there are things where your proof system will give the wrong answer, all right? So this is bad news, all right? All right. Everybody understand what we're trying to do? What I'm going to do now is I'm going to define a first order logic sentence compute that has free variables. It takes an integer J, it takes an integer I, it takes an integer Y, and it is true if and only if Java program J on input I outputs Y. All right? It's an amazing thing. Are you ready for it? All right. We're first going to make our lives a little easier, all right? Turing machine. You know what a Turing machine is? It's kind of simpler than a Java program, right? And what did we learn in our 2001 course? We learned how. So what we're going to do is we're going to do a slightly easier thing. You give me a Turing machine M, and I'm going to come up with a first order logic sentence. So this is a first order logic sentence that depends on M. You tell me M first, and I come up with the sentence, right? Versus up here, this is one sentence, while this is a first order logic sentence that depends on M. And what does it do? You give me an I and a Y, and it tells me what my fixed Turing machine M does on input Y, input I, right? You understand the difference between these two problems? The difference is here, it's a Turing machine we're talking about. Here, it's a Java program we're talking about. Here, it's a fixed Turing machine. Here, the Java program is part of the input. All right? So our goal is to do this one on the top, but we're going to first do this easier problem. Everybody agree it's an easier problem? All right?
Yeah.
So let's pretend we know how to do the easier problem, and I'm going to tell you how to do the harder problem. And after we do that on this page, the next page I'll tell you how to do this easier problem. All right? And first, let's go convert from this to this. All right? So suppose we know how to do this. All right. So let's remind things that we also have learned in this course, right? Remember what we did in test 2 is I gave you something that looked kind of like a Java program, and then we ran it through a compiler and it converted it into machine code. And then we took the machine code and we converted it into a compiler, into a Turing machine, right? Everybody agree that there's a mechanical way to take a Java program and convert it into a Turing machine. Everybody agree with that?
Yes, sir.
Excellent. All right. Here's another thing I want you to agree on. We just did it on the previous slides. There exists a thing called the universal Turing machine. And what do you do with it? You give it the description of a Turing machine and an input. And what it does is it simulates that Turing machine on that input. Everybody agree with that? Yes.
I think if we see these in an example, maybe they'll be easier to understand.
Well, this is some big fixed Turing machine. All right. And we did sort of cover it quickly in this course, or at least there were video. Actually, maybe I never talked about it this term, but there were videos that talked about it. All right.
Okay.
So, but let's just trust me. There exists a fixed, big, scary Turing machine, but it is a Turing machine. And what does it do? You give it 2 inputs. The first input is the description of a Turing machine. And you'd have to think, okay, how are we going to encode that? But let's just trust there's some ways that we're going to write down the description of a Turing machine, right? This universal Turing machine, remember, it has a tape where you give it its input. And you write it down in binary, right? Because this Turing machine is going to take binary input. And what does it take as input? It takes the description of a Turing machine as input, and it takes some input I as input, right? And what's this universal Turing machine going to do? It's going to look up the states of the Turing machine that it's described. It's going to look up the delta transition functions. It's going to run, it has one head, and it runs the head back and forth, back and forth, back and forth, right? Looking up, oh, what state I'm in? Oh, what do I transition? Oh, what's the character? Da, 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 da. It works very hard, right? And what it's going to do, in the end, what it does is exactly what the Turing machine that's being described does on the input that's being described. Right? Does that make sense?
So if the input was I, you have M of I as output? Like the final...
The input, there are 2 inputs. There's the
Yeah,
description
the M
of a
and the
Turing
I.
and the I. So both of them are given. This universal Turing machine has a tape, and on its tape we have 2 inputs: the description of a Turing machine and an input. And what is the output? It's what if I had run the M on the I, what output would I be given?
Oh, okay. So like the I in the output is written down from the I in the input. Okay.
All right, so here we go. Let's do it again. Here's a universal Turing machine. What is it? It's one big fixed Turing machine. And what do we write on the tape? We write an encoding of the Turing machine M, right? Here it's written on the tape, the coding for Turing machine M. And we write here the encoding for the input for M. And over here, what we're going to write is the output for M, right? And what does this universal Turing machine do? It has fixed rules. It comes over here and says, oh, M is in the start state. And M, oh, here's the input. What is M's character looking at? Great. Okay, what's M going to do? It runs over to the delta function and says, oh, if I'm in this state and I'm looking at this character, I go to that state. Okay, I'm going to change to that state. Oh, I'm going to write this character. And it just goes back and forth and it does what it's supposed to do. Right? Does that make sense?
Yeah, I get it, sir. It's just bigger than the one we just did before. Like, it's just bigger one. Okay.
Yeah. So what did we prove here? We're proving that there is a computational problem. Here at this slide. There exists a computational problem called the universal problem. And what does it do? It takes as input, the description of a Turing machine and an input. Right? And what is it supposed to output? Is what does the Turing machine that I described, what would it do on its input? And we're claiming that there exists a universal Turing machine that on all inputs, what does it do? Well, if you run the universal Turing machine on the description of a Turing machine and on an input, what the universal Turing machine does is it simulates the described Turing machine on the described input. Right? Does that make sense?
Yeah, I got it.
Right? And if people want, we could go over how to do this, but not today. In fact, I have videos, I have slides on how to do this. It's something that we were supposed to have covered. And why did we not cover it? Well, the videos were there, but I didn't cover them. I didn't do them in person in class, and it wasn't on the test, right? One problem with this method of teaching is that it's much more likely that things that aren't on the test fall between the cracks. All right, so now, what are we doing here? All right. So what I'm claiming, here's two things that I need you to remember from what you should have learned in this class, though maybe I failed at teaching you, right? The one thing is there's a compiler that takes the description of a Java program and outputs the description of a Turing machine, right? That you should believe. Another thing you should believe is that there exists, in fact, this shouldn't surprise you too much. Have you heard of compilers versus simulators, right? Is Java a compiled language or is it a simulated language? Do you know what I mean by that? A compiled language is you take the description of the Java program and you compile it into machine code, right? And then you run the machine code. A simulated program, if Java is simulated, then there's a simulator, a universal simulator that takes the description of the Java program and the description of the input, and it runs the Java program on the input, right? These are both things that you should be familiar with, right? Does that make sense? And that's all we're talking about, is we're talking about simulating Java, right? Remember up here, what do I want to do? I want to run, I have a description of a Java program and I want to run it on some input, right? So somehow I have to have something that simulates it. So what I'm going to do is I'm going to take the description of the Java program and I'm going to compile it into a Turing machine. And then I'm going to use my universal Turing machine to take the description of really basically of that Java program, and I run that Java program on the input. Right? Does that make sense? Right? So now, let's put these last two sentences in together. Let M prime be the universal Turing machine. I just called it M prime. Why? Because universal took up too much space and it would run off the end of the page. All right? Composing it gives me one Turing machine, M prime. What do I do to M prime? Well, actually, it's the two put together. What does M prime do? I give it the description of a Java program. I give it an input, and it runs that Java program on that input. Right? Everybody believe that that exists? Right? Do you guys see what I have right here? This is a laptop. Does anybody doubt that I could have Java code on this laptop and I could run it? Anybody debate that? No. You know
No.
that I have. No. All right. So this here, anybody debate that this is basically a Turing machine? Right? This here is a Turing machine. Right? All right. So what am I saying here? I'm saying there is a Turing machine M prime, which is my laptop. And what do? If I put in my laptop a description of a Java program, and I put in my laptop some input, then my laptop will run that Java program on the input. That's all I'm saying, right? Everybody agreed with that?
Yeah, yeah,
right? That's pretty straightforward, right?
yeah.
All right.
Yeah.
All right. So our goal is to come up with a logical statement that has these three inputs as integers, right? And so how do I do it? Well, up here, I'm going to, given a Turing machine, I'm going to make one logical statement, right? So I make the one logical statement based on this one. I have this fixed Turing machine, and I make one logical statement based on my Turing machine, right? And what is the logical, what are the inputs? Well, what is this Turing machine up here? What's this logical statement? It takes as description an I and a J and a Y, and wants to know, does my fixed M on that I output Y, right? So what am I doing? I have a fixed M prime, and I give it two things. I give it the description of an I, of a Java program in an I, and I give it a Y, right?
Sure. I have a quick question. So
Yeah.
what's the difference between M and M prime here? Like what could happen if you write M only instead of M prime to J and I, and you end up with an output for JI?
Well, M all the way through here is an arbitrary input. It's the I'm never actually building an M. M is just the description of a Turing machine.
Oh, so you made it M prime to show us the difference between the previous ones and the one you just wrote. Okay.
M prime, here, let's look at our concrete Turing. We got various Turing machines here. This page has many Turing machines. Let me show them all to you.
Like M is the laptop, right? M is the laptop, as what you said.
M prime is the laptop. All right, so let's just work. Let's just work on the laptop.
Okay.
M prime is the laptop, right? And what is M prime given? It's given the description of a Turing machine, and it's given
an input.
And an input, and it tells me what the Java program does on that input. Right?
Yes.
Right. So if everybody understands this, now my goal is to define a first order logic statement. And how are we going to do it? I'm going to first define a simpler first order logic sentence. What does that first order logic sentence do? Well, you give it a fixed Turing machine. There is a fixed Turing machine, which is the laptop. You take the laptop Turing machine and you build it into our first order logic statement, right? So our first order logic statement, when we build it, when we write down the characters for it, we're going to be using the description of the laptop, right?
Yeah, that's like when we make a Java program, we need to use the laptop to make it.
Yeah, we're going to build the first order logic statement that knows the description of the laptop. And what will it do? Well, we give it two things. We give it, in some ways, we give it these three things, right? And what will our first order logic statement do? it will say, what does our laptop do when you give it the description of a Java program and an input, right? What up here, what does this first order logic statement do? You build into it an M, and it tells you what that built-in M does on the input I, whether it gives you the output Y, right? And so that's what, now we build into it our laptop. And this is what it's going to do, right? It's going to say, hey, what will this laptop do if I give it this input? Well, what does the laptop do as you give it this input? What the laptop does is it asks, what does J do on I? Right? Does that make sense?
If I just have I'm just kind of confused about how you use the quantifiers and how you use your predicate statements. So before we had a lot of quantifiers, right? And then you tried to make a stronger predicate statement.
Yeah, we're getting there next page.
Oh, okay, gotcha. Okay.
Next page, right? Okay, hopefully you understood this, and if you don't, you can dwell on it. We're now going to change slides, and we're going to work on a different thing. We're going to pretend that we have a fixed Turing machine M, which may be the description of our laptop, and it's going to have two free variables, an integer I and an integer Y. And it's going to be true if our fixed Turing machine M on I outputs Y. Right? Everybody got that? So this is where we are. We're going to have a fixed first order logic sentence that says what? It says, does M on I output Y? Right? And I need to come up with a sentence that does that. Right? Just a reminder, here we have Turing machines. These are because I made these slides for 1090 people, and they might not know what a Turing machine is. So let's just remind us what a Turing machine is, right? It has a tape that has 0 1s on it. So it's the current configuration of the machine. If you stop the machine at some point in time, where is the machine at? Well, it has some binary string on its tape, right? And its head is somewhere, some cell. And there's some integer which tells me which state I'm in, right? I number the states 1, 2, 3, 4, 5. So there's some integer that tells me what state I'm in, right? And then there's a big transition function, right? A delta function. What does it do? It says, if I'm in this current state, right? If this is the state I'm looking at, I'm in, and I'm looking at a current character, then what state should I be in next? What character should I write on the tape? What direction should I move my head? Right? Everybody remember this?
Yeah, that was
Right?
already given. Yeah.
That's a Turing machine. All right. So now let's do this first order logic sentence. All right. What we're trying to say is I want to tell you, what is it supposed to say? It's supposed to say M on I outputs Y. That's what it's supposed to say. So how is it going to say that? It's going to say, because we need exists, right? So it's going to say there exists an integer C. What is C? It's an integer. Just saying there exists an integer. And what property does the integer have to have? Well, the integer C has to encode an entire computation. The one integer is going to encode an entire computation. And what's the computation going to be for? It's going to encode what does the Turing machine M do on input I? Does it output a Y? Right? Everybody see that? We're just going to encode, we're going to take the entire computation. We're going to take Turing machine M, we're going to run it on input I, and we're going to write down its entire computation, right? Then we're going to take that in computation and encode it as an integer. All right, so let's do that. There, I claim this is the entire computation. Why is that? Well, for every point in time from the start state to when the Turing machine halts, I'm going to tell you the state of the configuration of the Turing machine, right? What do I need to, what's happening at a particular point in time? Well, I'm in a particular state, right? Some state. And this is what's on the tape, right? And the head is somewhere, right? Everybody understand that this is the big Turing machine computation. Any questions about it? Right? I'm just trying to write down, I'm trying to translate everything into integers, right? So what is a computation? We already know what is a computation of a Turing machine is, right? It has points in time, and at a particular point in time, the Turing machine is in a particular state. So here, this is 1, 2, 4, 8, 12. It's in state 12, right? What's on the tape? Zeros in the first cell of the tape, zeros on the second cell of the tape, ones on the third cell of the tape, so forth. That's what's in the tape. Where's the head? The head happens to be on the fourth cell of the tape, right? So you see this entire line tells me the configuration of the Turing machine. Are people with that? Yeah, everybody good? All right. So now that's a configuration, and I need to convert this into an integer C. All right? How am I going to do that? Well, I don't like this little...
So the tape contents, right? How is it changing? How do you have different binary numbers?
Well, throughout time.
Is it based on the
Turing machine M is going to start. What is this? The Turing machine M starts in the start state with Y here on the here. What's time 1? That's the start state. What's the content of the tape?
Oh, I see.
That's Y, right? And then it starts running, right? What happened in the first step? It said, if I'm in this state and I'm looking at a 0, then go over to this state, write a 1 and move the head right. Right? That's what my Turing machine did. Right? At this point in time, it was in this state, right? And it said, hey, my head's here. I see a 0. If I see a 0 and I'm in this state, move your head, write a 1, move your head left, and go into this state. That's what the Turing machine did. Right? So we write down the entire computation. All right, people good with that? Then, well, what about these little red arrows? I don't know how to deal with red arrows. I'm an integer, right? So I'm going to replace the red arrow, right? I just shifted everything over, so I can put a 2 before the character that used to be a red arrow, right? It just stuck 2s in there. Everybody good with that? All right, another thing I don't like is these, how do I separate states from tape alphabet, right? How do I separate those? Well, I'm going to stick in 4s here and 3s there, right? So that how I know that 4 is the beginning of a time stop, and then I'm going to have a state up until I get a 3, and then I'm going to have then I'm going to have the tape contents up until the next 4. Right? People buy that? And then what about all these commas? I don't like commas. So we get rid of the commas and we squish everything together. Right there, I just got rid of the commas. And then we stick them together. And what do we get? We get an integer. Right? Everybody buy this?
So there's 3 steps to end up with an integer,
A lot of steps. I don't know.
right?
I started off with a
Oh, like
computation.
kind of.
I put in the 2's.
Yeah, then
I put in the 3's and the 4's. I got rid of the commas. I stuck them together.
Okay.
Right?
There's more than that. Okay.
Right? But it wasn't that hard. But everybody see how, what do I have here? This is an integer encoding computation M running on input I.
I have a question about the specifics of the Turing machine. So I know we just wrote like a computation for a Turing machine M, but do we need to quantify like the tape content, the tape alphabet is bound like this, or the length
this
of the
no
tape
no
is
no
bound with...
no. We have a fixed Turing machine.
Oh,
right here, the sub M is a fixed Turing machine, and
Okay.
I'm going to tell you right now that the tape alphabet is 0, 1. Right? Why do I know it's 0, 1? It's because I got all 0, 1s here. Right? So M is a fixed Turing machine with 0, 1 input tape.
I just meant like in terms, like, you know how you play the game and then like the adversary might give you like, and then we didn't write that down, so I might break the proof.
Yeah, but here, where did M come from? M came from over here. Oops, somewhere M came from. It's a fixed Turing machine that describes my laptop, and
Gotcha.
And we know it's good. Oh, we're really lost. We are doing hugely expressive. So we are here. All right, everybody got us here?
Sir, so when you change the numbers to 2, right? So
Yeah.
I remember you told us before that the Turing machine only accepts zeros, and so how are we allowed to change it to 2, like in this universal language here?
I'm just trying to, the Turing machine, this is the Turing machine, right? The Turing machine has a 0, 1 tape. The Turing machine has states, and I've numbered the states and I've written down their numbers in binary, right? This is the Turing machine.
Okay.
Now my goal is to come up with an integer C, one integer C that encodes this entire computation. Right?
Oh, I see. So you use the Turing machine 0, 1s only. Then when you, after you finish using it, then we do the other steps.
Yeah.
Okay.
Yeah. The reason the Turing machine's only 0 and 1 is so that when I introduce 2, it's a new thing. Right? 2, what's 2 for? 2 is to tell me where the head is. What's 3 and 4 for? 3 and 4 are to separate these blocks. Right? And then I stick them together.
Mm-hmm.
Now I have an integer. Now the Turing machine wouldn't know what to do with this integer, but it's okay. This integer is encoding a computation by the Turing machine. Right?
Can you show me what the separation was?
Sorry, show you what is?
No, separation on the previous slide.
Oh, here, right here, let's do it again. The Turing machine, that's a Turing machine computation, right? You got that? All right. So I need to represent this by a single integer, right? And I'm allowed to do it however I want. This is Jeff. Jeff made this up, right? As George will tell you, you won't find this in any book. Jeff made this up, all right? You take this entire Turing machine and actually, let me tell you, when Gödel encodes things with prime numbers and does really scary things, right? I've never seen this encoding I'm sure somebody's done it before, but I made it up myself. Why? Because I didn't want to teach you about weird prime numbers. So I'm going to teach you this encoding. And it's Jeff's encoding, all right? So here, we started off with the description of a computation, and I made sure that the description of the computation, what does it have? It has zeros and ones, it has columns, and it has locations of heads, right? So now I want to encode this. How do I encode it? Well, I'm going to take every head location and I'm going to replace it with the character 2, right? I just did that. Now I have to separate out these various lines of these various time steps, and I have to separate out the state from the tape, right? I have to separate them. So I'm going to separate them with 3s and 4s, right? Because everything else was 0s and 1s. So I can use 3. I can just do that. I can just put 3s and 4s in there, right? And these commas.
Sir, so would it be 3 or 4 normal?
What?
Like 3 or 4s or anything rather than 0 and 1s and 2?
Yeah. I just did 3 and 4. If you ask why
okay.
3, well, why not 3? It's right.
Yeah. Okay.
Right. Now the commas. Do the commas matter? Well, each of these numbers is a digit 0, 1, 0, 1, or 2, right? So I don't need to know that there's a comma between them because they're nicely just 0s, 1s, and 2s. So I can just remove them. Bang, they're gone. Right? And then here are all these digits. What do I do with all these digits? I stick them together. Now I'm taking of this integer. What base am I? This is base 10, right? What was my trick? When I was over here, I was in base 2, right? But then I stuck in random integers, random characters, and now I'm in base 10, right? But it's an integer. It's an integer base 10, and its characters encode something. Is everybody good? All right. So now what do we need to say? Somehow we need to say C is an integer that encodes a valid computation for our fixed Turing machine M running on some input I and some output Y. We need to be able to say that in first order logic about this integer. All right, so let's think about how we say it. Well, there are various things we have to say. We have to say at the first time step, the initial configuration, is that what you would have for our fixed Turing machine M on input Y, right? So we got to be in the start state. The head has to be at the beginning. We have to have Y on the tape, right? We have to say that. That has to be true, right? What else has to be true? We need that for every time step, we need that the Turing machine M takes a legal M, that their integer is encoding a legal step for our Turing machine, right? We need to say that. What else do we have to say? We have to say the final configuration. Well, the Turing machine M has to be in M's halt state, and Y has to be written on the tape, right? Everybody agreeing with this? All right. So that's
and the whole thing is just like when it completes, right? It just doesn't do anything else, right?
Yeah, I'm just saying, what does it mean for M to have a valid computation? I mean, it starts in the start state, and it ends in a halt state, and it has Y on the tape at the end, right? I'm not saying anything challenging here, right? All right, so I keep doing the hard parts, right? I drop things that you should be able to do by yourself, right? Now, what do we want to say? We want to say here's a for all statement, right? We want to say for every time step, we have to say that we're taking a valid step, right? Now, here's a funny trick. We can't talk about a time step, but we can instead, we're going to set, let I1, J1, K1, all these indexes, let them be integers. All right? This is a for all statement for all values of these integers, right? These are indexes. And what do we need to be true for them all? Well, we need them to appear in this order. So these are all integers that need to appear in this order. And we need that each of the i's, here there's an I there and an I there and an I there. If you go into our C and you ask what is the ith digit, you need to be able to say the i's encode 4s. Why? Because 4 was the beginning of a time step, and then the next 4 will be the beginning of the next time step, and the next 4 will be the end of that time step, right? So the i's are grabbing our time steps, right? So we're saying we want to say for all i's that are indexing 4-digit 4s, because those are going to be our time steps, right? And what are the j's doing? The j's are in between, and they have to index the separation between the state and the Turing machine. Between the state and the contents of the tape, right? People with me there? And what is the K index? K is indexing a 2, so it's telling me where the head is, right? Does that make sense? I have to be able to say for all of these things, right? And what do I also have to be able to say? I have to say for every other index that's in between these, we're indexing a 0 or a 1, right? Because we don't want extra time steps in there. This is just one clean 2 time steps, right? Everybody understand what we're doing here? Right? Excellent. All right. Now you still might say we haven't gotten to logic yet. You're still writing things in English. In the end, there'll be no English. So somehow, now that I have this I1 and this I1 and this J1, right? What are they doing? They're sandwiching the state. Remember, this was the beginning of the state. This was the end of the state. So we have to be able to cut out the state, right? We have to cut out 1, 1, 0, 1. We have to determine what state we're in, right? So let's do some math. Well, let's take C, right? C is our big number, and divide it by 10 to the J, right? I told you we could do multiplication. Well, if you can do multiplication, you can do division. All right. So, and we can do it, and we're doing positive integers. So you can able to do round. Everything is an integer. So it rounds down to the nearest integer, right? What happens if you take C and you divide it by 10 to the J? What happens is we kill off J characters, right? And so what is this integer that we get? Well, it's the integer C with everything past J cut off. Everybody good with that? Right? All right.
So the first part 4, 1, 0, 3, 2, the bottom answer, the final answer you got.
Yeah.
Right here. So the beginning of it, did you take off 1, 1, 0, 1?
See this J right here, the J1?
Yeah, the 3, right? It points to 3.
Yeah, it's pointing at 3. So if I divide by 2 to this J, right? If I divide by 10, so not 2, 10. If I divide by 10, what happens? The bottom digit disappears, right?
Okay.
If I have 58 and I divide by 10, what do you get? You get 5. Right? What's 58 divided by 10?
So here it's 10 to the power of 3, right?
Yeah, it's 10. If I divide by 10, lose 1 digit. You divide by 100, you lose another digit. You divide by 1,000, you lose another digit. I divide by 10 to the j, I lose j digits.
Oh, okay.
Right? That's all I'm doing is I'm killing the low order j digits. Right? Does that make sense?
Yeah, I see it. You got rid
All
of
right.
the zeros. Yeah, I see it.
I got rid of all this stuff. All that stuff I got rid of.
Yeah, you
All
only
right.
kept the important ones. Okay.
Yeah. Now I'm going to do something weirder. Now I'm going to do this I up here, the I that's indexing the 4. I'm going to first divide by 10 to that I, or I minus 1. You have to figure out which, right? And that's going to get rid of, let's see, what are we doing? Divide by this, and oh yeah, I want to kill everything. I don't want to kill the 4. I want to kill everything before the 4. All right, before we killed the 3 and below. Now I'm going to kill the 4 and, oh, not going to kill the 4. I'm going to kill everybody below the 4. All right. So I divide by 10 to the I minus 1, and that kills everybody below the 4. And then I'm going to multiply by 10 to the 4. And that's going to give me 4 zeros. Right? Here, what's this number? What's my B? My B is kill everybody that's digit 3 and below. Right? And then everybody that's below 4, don't kill it, but 0 it out. Right? Everybody see how we do that? Here, everybody that was below 3 is gone. And everybody that's below the 4 is zeroed. You good?
There's just so many numbers to look at.
All right.
Like,
All you have to know, all you have to get, this won't be on the test. All you have to get is that there's some math which can cut out. Here's what am I doing? I'm now subtracting A minus B. And what do I get? I get 1011. What is that? Those are the digits. That's the number between the I and the J. Right?
I have a question. You didn't use like mod or anything because you didn't define as an operator, right?
Yeah, I could have done mod. It boils down to the same.
sir, you said between I and J, right? And you got 1011, right? But but between I and J, you have 1101.
Dude, I'm dyslexic. That is certainly a typo. Oh yeah, here it's 1101. All right, so good. Here's a typo. Let's fix that. Good.
Okay, now makes sense.
All right, now everybody happy?
Yeah, because I was looking at the 1001 at the end. I was like, wow.
Yeah, that's just more extra scary. Everybody good? How we just cut those out, right? So now we have all of these indexes and we cut out everything we need. Now we know the old state, we know the new state, we know the digit that the head was looking at, right? Here's the state at time t, right? Here's the tape at time t. Here's the head is looking at a 0, right? Then at our next time step, we know the new state. We know the new tape. We know which digit the head is looking at, right? We can cut those all out, right? And then, right, we've memorized M, right? M is a fixed Turing machine. So we can write down a fixed statement that's set with ands and ors. Fixed statement. We're in this state and we have this head, so we go over to this state. Or we're in this state and we have this head, so we move over to this state, right? Use ands and ors. We can write down that we're taking a legal transition move, right? Everybody good? And we're also saying that the tape doesn't change where the head's, except at the spot where the head changed the tape, nothing else changed, right? So that's just another for all statement, right? And that's it, right? That's it, right? What did we define? We defined it, we defined a logical statement that has J is an integer, I is an integer, Y is an integer, and it tells you, does Java program I on input I, output Y, right? It's just amazing, right? How did you like that?
So now we can basically just make a binary number, and we can like walk through the number to convert it to integer after what we just learned today.
Sure. Right, here we just linked. What did we do? We just linked the Java programs, which is computer science, to Turing machines, which is computer science from the 30s, to logic, which is 1090, and we showed that they're all linked together. So if you didn't believe that first order logic is a powerful thing, right? It's as powerful as computation. And that's what Gödel proved. When Gödel was doing his, in order for Gödel to prove this, it was before, you have to say Gödel was completely amazing. Turing was amazing, but Gödel was more amazing, because Gödel came up with this, in order to prove his incompleteness theorem, he had to encode computation into, like we did here, he had to encode it into his first order logic statements. And he had to do it before they even had a model of computation, right? He did this before Turing did his stuff, right? And that is what we're going to do today, right? Because we're done for today.